Start recording now. And I'll go ahead and get started with the first presentation. Okay, so the two topics that I want to cover today are miscibility and thermodynamic cycles. So these were both talked about a little bit kind of in the beginning, and I think pretty much during last week's lectures. So to kind of go over miscibility first, we started off this discussion in lecture by considering the free energy of mixing. And the place that we got the free energy of mixing equation from was by first looking at entropy of mixing. And this is kind of just a recap of stuff that was discussed like way earlier in the course. But if you have a setup in which you have a compartment that has both A and B molecules, and then you allow both of them to mix after both being in like pure states beforehand, you will get an equation for mixing that looks roughly like this. And just to give everyone like a quick refresher on what some of these like symbols indicate, XA refers to the mole fraction of A molecules. So mole fraction is a unitless quantity. It just basically means what fraction of the molecules or moles in a given composition are of type A, and this mole fraction of B is just what percentage of this or what fraction of this is B. So this gave us the entropy of mixing in this case, but when we're considering the free energy of mixing, we also have to think about the delta H term. Now, previously, when we looked at this setup, we always assumed that none of the molecules were interacting. And so in that case, it didn't matter what delta H was, because it would always just be assumed to be zero. But if we want to look at more interesting relationships of what happens when two things are mixed, we know that this is not always the result. For instance, if you mix oil and water, it very much does not look like this. And that's why considering delta H can kind of lead to interesting conclusions. And that was the point of the previous lectures in the course so far. So just two things I wanted to point out here, which is that number one, in general, if you're looking at mixing, this is something that always increases entropy. You can think about this intuitively in the sense that if you're mixing two things, that's like more disorder, it's more chaos. But also you can just look at the equation, and that tells you that if you're mixing two things, entropy always goes up. So at any given temperature, if you keep increasing the temperature, that makes the favorability of mixing just increase more. And the next thing that we need to consider is just that if we think of a good way to capture or model delta H, then we can essentially represent lots of different types of behavior. So with that said, I'll go directly into how you can calculate delta H for mixing. And I think a good way to start off this discussion of how to calculate delta H is to imagine the system in like a before and after picture, and then use that to calculate the change in interaction energy that occurs. So this is kind of what the before picture looks like for the system. You essentially just have A molecules interacting with each other, and you would similarly have B molecules only interacting with each other. And between each two set of A and A molecules or B and B molecules, there would be some type of interaction energy. It doesn't matter what it exactly is, but there's just some type of interaction energy. And then mixing occurs, and then you end up with a system that looks more like this, where you have a lot of A and B interactions. And the way that this was quantified in lecture is you looked at something like this. And the description that was given was that if you do this thought experiment in which you have a system that is like purely blue molecules and a system that is purely white molecules, and then you have two molecules trade places and you measure the change in energy as a result of this process, then you can end up with delta H. And then we also just say, like, let's call this delta H 2 gamma because we're moving two molecules and we want to divide by 2 so we can get an average of what is the change if you moved only one molecule. If you want to think about this in terms of more of the formula that's involved, you can think of this as if you start off with two homotypic interactions, so A and A, B and B, and if you break both of those interactions and you instead form two A and B interactions, the total change in energy that occurs as a result of that process can be thought of to be 2 gamma. And so if you only want the result of one A and B interaction, that would just roughly be gamma. If all that doesn't quite make sense, you don't have to worry about the fine details too much, but you just have to imagine or just understand that this parameter gamma, what it's used to represent is the idea of an A and B interaction forming as the difference from what it was occurring in the pure state. So if we're going from a state that's purely A and purely B to a state in which they're mixed, gamma represents the change in interaction for one pair of molecules A and B. And so once we have that understood, the next question we have is, okay, so we know that Gamma represents the amount of change in energy for one A and B interaction forming, but how many A and B interactions typically form. And the way we can do this is by just counting the number of A molecules, which we know is N1 because that's in the setup of our first equation. And then we also consider the probability of finding a B molecule. And we can substitute the mole fraction of B here because the mole fraction of B in this case would just be the number of B molecules divided by the total number of molecules in the entire system. So that's like a rough way to give a probability of finding a B molecule. And if you multiply those two things, that gives you roughly the number of A and B interactions we would expect as we're mixing. And this kind of makes sense because if N1 was small, meaning that if we had very few A molecules, this would be a small number. And similarly, if B were really small, meaning that N2 were really small, then we would also have a small number of interactions. And then if you multiply this by gamma, you will get delta H. And that's what was shown in lecture. And so now that we have delta H, and since we had derived delta S from way back several lectures ago, we can now get our final delta G mixing equation that looks like this. This was also taken from your lecture slides. And this gives us this interesting graph here, which I want to spend a little bit of time just talking about how to interpret this. So first off, we can note what the two axes represent here. So this x-axis, representing x1, represents what percentage of the two things that we're mixing together are A. So there is a system in which we have pure A molecules and pure B molecules coming together. X1 represents what fraction of that initial system is A. So over here, you have purely A. Over here, you have purely B. And then delta G of mixing just quantifies, probably in joules or kilojoules, the free energy change as a result of mixing. And the way you can interpret this graph is if you start off with some concentration of A and some concentration of B, let's say it's like a 60-40 mixture, and you mix both two things incredibly thoroughly, and you get a mixture that's as homogeneous as possible, then depending on whatever your gamma parameter is, you will end up with a free energy that's somewhere here, just depending on whatever gamma is. And then based on that free energy, it should tell you which movement the system takes from there. So for instance, if you have a 60-40 mix and your gamma is 1 kT, you'd end up with a free energy around here. And so if you end up with a free energy that's, I'd say this is like roughly 0.42, negative 0.42, you might ask, well, the minimum looks like it's over here. So why won't the system just drift towards this? And the reason for that is if you imagine this mixture of A and B as occurring in lots of different bubbles, if all of your bubbles are 60-40 A and B, and then one of them decides to become 50-50 A and B, it needs extra B molecules to get there, which it would be borrowing from, you can, I guess, another bubble. So any type of movement that occurs in this direction forces some other part of the system to move in this other direction. And that's why it can't really move anywhere beyond just here. So it kind of is just stuck there. And so we can kind of interpret each one of these curves. So for example, the gamma equals 0 and the gamma equals kT curves are relatively similar because whatever you start off with, once you mix it, you'll end up with some free energy. And you can't really change it much because trying to approach the 50-50 mixture in which you will have minimum free energy requires you to either borrow more A or more B from some other part of the system. And whenever you do that, you will just end up increasing the free energy in the other place. And that's why you'll kind of just be stuck wherever you started. And so just to make sure everyone's understanding this correctly, I have kind of a poll question for everyone, which you can respond to in the chat just by typing A, B, or C, depending on what you think the answer is. But if you started off with an x1 of 0.2 and you had a gamma of kT, what would be the resulting free energy of mixing? Would it be 0, negative 4.5, or negative 0.35? You just type in the chat whatever you think the answer is. I hope everyone can see these numbers. Any thoughts on what the delta G of mixing would be? Okay, yeah, C. So there's one vote for C. And yeah, that is true. The answer in this case is C, because if you start off with a mole fraction x1 of 0.2, and you look at the kT curve over here, this is roughly negative 0.35. And this is pretty much where the system will be, because even though the minimum value for the kT curve is at 50-50, since you're only starting with 20% A, it will be really hard to move towards a system that's 50% A and 50% B because you only have a fixed amount of A to begin with. And so forming a 50-50 mix would require you to borrow A from other parts of the system. So the free energy would pretty much be somewhere here. And that's the best that the system can do given the starting concentrations, I guess is the main point. And then for these other two curves, the two gamma KT curves, we can further analyze what they mean. So for instance, the gamma equals 2 KT curve, this one is special because it has this red point that's indicated here. This is what's known as the critical point. And the reason why this curve is interesting is because in this range where things look relatively flat, so I guess this is like 0.75 to maybe 0.25, within this range of x1, any kind of concentration of two mixtures that you mix together will achieve relatively the same free energy. And this is also significant because you can have a lot of fluctuations and the system will probably not resist those fluctuations. So even if you had a 50-50 mixture of A and B, if you were to move the system in a way such that you create maybe lots of different bubbles that are now 60-40, having a 60-40 split has relatively the same free energy of mixing. So you're allowing the system to compartmentalize itself in 60-40 mixtures in a way that the free energy doesn't change. So it can essentially do a wide range of behavior and the free energy will still be the same. So that's why when Professor Grove says that there's lots of interesting phenomena that can occur near critical points, that's what he means, because there are lots of different things that have relatively the same free energy. So they're all kind of allowed. Whereas in other parts of the system, any type of small movement would usually have some type of penalty in terms of free energy. So it's discouraged. And then what happens with gamma equals 3 KT is a pretty interesting scenario because in this case, the gamma parameter is pretty high, meaning that if you started with a mixture that's, say, 60% A and 40% B, then when you mix the two together really thoroughly and you try to achieve a homogeneous mixture, you'll actually end up with a positive free energy, meaning that the resulting mixture is unhappy or that it's energetically unfavorable. And once you're here, there will be a driving force to get to the minimum points, which are here and here. And this is what's known as phase separation, because if you mix A and B together, you will end up with some type of separation in which pockets of your mixture have very high concentration of A and low concentration of B, and then some other pockets will have very high concentration of B and low concentration of A. And I think a good way to think about this or visualize this is this one diagram here. I got this from a YouTube video that has like a simulation with different concentrations, and I've linked that in the notes for this presentation if you want to play around with it yourself. But if you imagine this type of scenario in which you start off with a lot of A and then also a little bit of B, you mix the two together, you'll end up with a phase separation like this, where some parts of the solution look like this, where there's a ton of A mixed in with a little bit of B. And then you'll also see parts of the solution that have a lot of B and a little bit of A. And the reason why there's a lot more of the alpha phase instead of the beta phase is just because you started off with a lot more A. If you had started off with a lot more B, then you'd see a lot more of the beta phase. But that's just how the phase separation works. Any questions so far? Okay, I'll continue. And so the next aspect of phase separation admissibility was this graph. And this is the last diagram I want to show you before moving on to thermodynamic cycles. But the idea here is that pretty much all of these lines can be generated by taking different derivatives of the free energy of mixing function. So first of all, this line right here, this represents the free energy of mixing for the gamma equals 3 KT parameter. It's supposed to be roughly reconstructed. And then this binodal graph here, this line represents the first derivative and the spinodal represents the second derivative. And then notice that the delta G of mixing equation is a function of two variables, t and x1. So you can imagine that if you take the derivative of this with respect to x1, you're going to end up with some expression that has both t and also x1 somewhere in there. And so when we're looking at these graphs and we're saying that this is dg over dx1 equal to 0, what this graph is saying is that we consider all the pairs or like all the coordinate pairs of x1 and t where the derivative is equal to 0. And in the case of the spinol, all the pairs x1 and t where the second derivative is equal to 0. And these two graphs can tell us some pretty interesting things. So when we're looking at this entire diagram as a whole, notice that the axes are now x1, which is the composition, and also temperature. And remember when I said earlier, at high temperatures, you're rewarding the entropy term in free energy of mixing. At high temperatures, you have a homogeneous mixture, regardless of how much A and B you have, because at high temperatures, you're rewarding the entropy term in the free energy of mixing, which is why everything up here is homogeneous. But then at low temperatures, and also within the bounds of this binodal line, you have phase separation, which is what I showed you in the last slide between the green and blue circles. And we can also think about this a little bit further in the case that let's consider a very specific temperature. So it doesn't matter what this temperature is. Let's say it could be 100 kelvins, could be like 200 kelvins. But at this temperature, notice that the binodal has two minimum points. So we know that at this temperature, the binodal has a minimum free energy at x1 of, let's say this is 0.7, and maybe an x1 of 0.3. And so I think this is sometimes referred to as like the coexistence line or like the coexistent phase. But what that usually means is that whatever concentration of X1 that you start out with, if you're at this temperature, there will be a driving force by the system to kind of split your states to get to some of it in this equilibrium and some of it in this equilibrium. And so what that happens, practically speaking, is let's say you start off with an X1 of maybe 50-50 A and B. Then what's going to happen is that there is a driving force by the system to achieve local concentrations where it's 70-30 A and B, and then 30-70 A and B. That's just what this graph is trying to show you, that no matter where you end up with X1, you kind of just draw a horizontal line corresponding to the temperature, and that tells you your two equilibrium concentrations for A and B that are allowed. So that's what the binodal curve shows you. In lecture, it was also mentioned that the spinodal, the region between the binodal and the spinodal refers to like this metastable region. I think just the only comment I want to make there is that because the spinodal is the line for which the second derivative is equal to 0, the main interpretation I would give to that is if you think about calculus, when you're calculating the second derivative, usually it was to find an inflection point, which is when the graph goes from concave up to concave down. And I think the point that Professor Groves was trying to make in lecture is that if you have a graph that's concave up, where it's like, like an open bowl shaped, then there is this kind of restoring force where if there's a small fluctuation, then the increase in free energy as a result of that fluctuation will cause it to return to its original point. And so in that sense, it's stable. But if it's concave down, which is more shaped like a hill, then if you have a little bit of a fluctuation, then it will just cause it to kind of go out of control in the other direction. And I think you could probably understand that as just, if you were to place a ball, like where would it roll? If you have a bowl, it would probably just like roll downwards. But that's like the main interpretation of metastable. So yeah, I think that's all I had on miscibility. So before I go to thermodynamic cycles, does anyone have any questions so far? Okay, so now I'll go over thermodynamic cycles. So the first thing I want to talk about is state variables and functions. So the textbook definition of a state variable or a state function is just something or a function in which the value doesn't really depend on the path that you took to get there. And I think the definition doesn't really do as much justice as just looking at some examples of state variables and functions. So an example would be delta H or delta S or delta G. And the reason why these are state functions is because they involve state variables. And if you think about a state variable, these are things like H, S, like enthalpy, entropy, and Gibbs free energy, because they really only depend on your current position. They don't really depend on the path that's taken to get there. Another example of a state variable would be something like temperature. It doesn't matter how you got water to 50 degrees Celsius. Water at 50 degrees Celsius is kind of independent of whatever steps you took to get it there. I think another way to think about this is if you think about difference in elevation as a state function, then it doesn't really matter which path you took to get to the summit, because whichever path you take, the difference between the summit and the base in terms of the elevation will be the same. And so if you look at path Y, you might end up going down in elevation and maybe up in elevation depending on some parts of this journey, but at the end, the change in elevation will be the same. And that's the idea that we're going to borrow from when we're thinking about thermodynamic cycles. And I think this is in number 1 of your homework. So if we consider a thermodynamic cycle, there is usually the setup for a problem like this is that there is some generalized set of reactions, usually like some letters combining to another letter. And usually the setup for a problem like this is that there is some delta G formation that is unknown that we want to figure out. And normally what we would do is just do delta GF of the product minus delta GF of all the reactants. But if those things are not available to us, we have to then consider, instead of a path like X in the last slide, something like path Y. And so what we can do is construct a cycle of all the intermediate reactions to get to this final position. So if we think about our starting materials, one of the first processes that occurs is you have V splitting into two components of U. And so you can consider a reaction like this. And then the next thing that could occur is you have two of U combining with Y to form T. And then you'd be left with W and T. And then you have this reaction over here, which is W and T combined to Z. And so then as a result of taking these 3 steps, you end up at Z. And because we're working with delta G, which is a state function, this means that it doesn't matter what steps you took to get to Z. If you just add up all the changes in heats of formation or delta G of formation that you took to get there, you'll get the same answer as if you had gone from here to here directly. And so to compute this unknown delta G of formation, you just simply sum up all the values that were taken in this process, and you would end up with roughly negative 125 kilojoules per mole for this scenario. And then just very quickly, there's also an example that's given in your textbook for the reaction of glucose formation, in which we want to calculate delta G, the free energy, the standard free energy of formation for glucose, but we can't get there directly. However, we do know the standard free energy is of formation for CO2 and H2O, and we also know it for glucose combustion. And so if we start with these starting materials, the first thing that we can do right off the bat is we know the free energy of formation for CO2. So we can combine carbon and oxygen, and that's one step in the cycle. And then the next thing that we can do is combine oxygen and hydrogen to get the free energy of formation of water. That's another step in the cycle. And then finally, we have water and carbon dioxide, which are the products of combustion. And essentially, we want the reverse of the combustion reaction. So instead of going from glucose to water and carbon dioxide, we're going from water and carbon dioxide back to glucose. So we just take the negative of the glucose combustion reaction, and we end up with a complete cycle going from starting materials to glucose and oxygen. And so once again, if you were to just sum all these steps, you will end up with a free energy of formation of roughly negative 920 kilojoules. So hopefully this makes sense on how to approach problem 1 in your homework and just elucidates how thermodynamic cycles work in general. So that's all I had for my slides. So the next tutor can feel free to begin.
Hello, I'm Shaya. I'm going to walk through some of the general kinetics stuff. Oh, I'm not sharing my screen. Okay, can you guys see my screen? One of you could just like unmute yourselves.
Yeah, we can see it.
Oh, great. Okay, thank you. Okay, yeah, so basically kinetics is just the rate of things, how fast things go. And it's really interesting. It's like through 2/3 of the course, and this is the first time we're talking about time in a reaction. So we've spent a lot of time going through, you know, the entropy and enthalpy and all of that, but none of them tell you how fast the reaction will proceed. So kinetics, and basically it's for a very simple reaction going from A to product B, you're going to get that the rate of decay of A is equal to the rate of accumulation of the product B. And that's for an equation where the stoichiometric coefficients are 1. And so if we did a similar example with, say, 3 molecules of A needed to make 1 molecule of B, we could apply the same equation to get something like this. And the reason we account for stoichiometric equations or coefficients in a rate equation is that intuitively we can see that we need 3 molecules of A to make B. So we need a molecule of B the rate of making one molecule of B is equivalent to the rate of using up 3 molecules of A. So those rates are equivalent. And so we can try making a generalized rate equation for this reaction. So we know that this corresponds to some constant K times some times the concentration of A. And we know that this rate is proportional to the concentration of A by this constant. And we don't know what this constant is. So if we can try to get all the A's to one side, we can rearrange this equation to get this. And if we integrated both sides, this one with respect to the concentration of A, so here's the generalized concentration term. This is the concentration A naught when the reaction just starts. And here again, T equals 0, because we're integrating with respect to time. And this is a generalized T. And equating these two, we get that ln of the concentration of A at any time T minus ln of A naught is going to be equal to negative 3 kT. And then just by simplifying by taking the exponent of both sides, we get that A over A naught equals e to the power of minus 3 kT. And this is a generalized equation that we can use for first order reactions, for second, and so on. So this is the basic kind of way that we walk through getting a generalized rate equation. So we can see that our rates are dependent on the concentration. And the reason that is that a rate of a reaction is proportional to the rate of collision between 2 or more molecules. In this case, let's take 2 molecules, A and B. And so the rate of collision is dependent on the probability of finding each of those molecules in a space. And that probability, as we know from earlier chapters talking about entropy and stuff, that is proportional to the concentration of the reactants themselves. So we can assume that the rate of reaction is proportional to the probability of one molecule of reactant times another molecule of reactant, depending on how many molecules of reactants are required for the reaction to proceed. And so in an A-B collision system, it's going to be the concentration of A times the concentration of B. And in, say, an AA collision system, it would be just the concentration of A squared. And so the proportionality constant, K, also known as the rate constant, represents this frequency of collisions. And it also represents, and this is super ambiguous, but we're going to talk about it later in the chapter, it also represents the productivity of collisions, because not every collision is going to result in a successful reaction going forward. Not every collision between a molecule of, say, A and B in a system is going to be productive. So K takes into account all of that. And so we can now talk about the different orders of reaction, which is just, similar to the systems we talked about earlier. We can imagine like lots of molecules of, say, A to be in one system, or A and B in this case to be in a closed system. So we can now infer the order of each reaction. And the reaction order is just the sum of exponents in your rate equation. I apologize, my handwriting is quite terrible. But so in a first order reaction, all we have is molecules of A, but we don't need one molecule of A to collide with another molecule of A. We just need a single like molecule of A. And this is not super common. The most common example of it is radioactive decay. So we have dA dt corresponding to some constant K times the concentration of A, because that is the only reactant. And in a second order reaction, it's a similar thing. So we can do a dA over dt equals negative K, and in this case we have A and B on which the reaction depends. So this is the generalized rate equation that we're going to get. In a third order reaction, very similar thing, we can just extend that logic to get, in this case, 2 molecules of A needed to react. So it's going to be concentration of A squared times concentration of B. And if we had to write out like a stoichiometric equation, it would be 2A plus B, giving you 1 molecule of C. And a zero order reaction is a case where the concentration of A is much, much larger than, in this case, Z, which is a catalyst. So your concentration of A is so high that your reaction isn't dependent on A at all. So your order of reaction is going to be 0, and this is kind of the generalized rate equation that you will get. Any questions on any of that? I think Florence is going to go into depth of deriving rate equations. Okay, I can stop sharing my screen.
Okay, so I will share my screen. Oh, sorry. Yes, so I'm going to be deriving the integrated forms for the rate laws. So as Shreya showed you just 5 minutes ago, these are the rate laws for different order reactions. So for zero order, we have this term because the concentration of A is, for example, if we're reacting with a catalyst, and the concentration of A is big, then the concentration of A should not change much. So it's approximately constant, and that's why we have this negative K term here. And then we have a first order reaction and then a second order reaction. So these equations here show us the rate of change of the concentration of the reactant, but it doesn't tell us the concentration at a given time. So my goal here is to find the concentration at a given time t. And essentially, in every case here, it's pretty simple. It's just integrating the expressions and trying not to make calculus mistakes. Yes. So in a zero order reaction, we have this rate law. So the change in concentration over time is just negative the proportionality constant. So the idea is to isolate A into the concentration and to isolate the time term. So here we can just simply move dt over to the right. And then afterwards, we want the actual concentration, not the change in concentration. So we should integrate. So let me color code this better. So integrating, we're starting from the initial concentration at time t equals 0. So that is concentration of A and with a subscript 0. And then time equals 0 and some general time t, and then to some general concentration A at some time t. Now after integrating, you will get this term. Oops. So A minus the initial concentration minus equals minus kt. And after rearranging, you should get this term. So notice that here at any given time, the concentration of A at for a zero order reaction is this function is linear. and it decreased. This concentration decreases linearly over time. Similarly, for a first order reaction, we have this rate law here, and again, the idea is to isolate A and to do integration. So isolating A, we should move over or divide by the concentration of A and then multiply by dt. Then again, we do this same bounds. And then the integral of 1 over x, I believe, is log of x. So log of A from A0 to A, and then again, minus kt. So here we would get ln of A minus ln of the initial concentration minus kt. But notice that we can, the difference of two logs, you can just put it into one term like this. And then since we want to find the actual function, the concentration, we should isolate concentration of A. And we do this by exponentiating. So this way the logs cancel out. So then we would get concentration of A is equal to, and then moving the initial concentration over, we will get e to the minus kt. So in this case, this is different from the zero order reaction because the concentration decreases over time. So for this case, there's a pretty interesting property, which is that you can also find the concentration of product here using this term over here, or oops, yes. Because, well, stoichiometrically, we're making, for every one product C, we need exactly one of the reactant A. So that tells us that every molecule A that is converted, must be converted to C. So then the concentration of C must be the initial concentration minus the concentration of A at that given time. So we know the concentration of A at any given time from our expression above. So just plugging this in, we get the initial concentration times e to the minus kt. And then again, you can simplify this term. So again, this concentration of product, it also increases exponentially, but flattens out as t tends to infinity. For a second reaction, we have a different case. So the case we're going to talk about right now is for if we have the same reactant type. So two A's make one C. The other case is two different types of reactants, A and B, and that's a lot more complicated, but we will do this one first. So yes. So again, moving this over, I will do this quickly since I think you've seen it already a lot of times. Yes, so 0 to t, that so the integral of 1 over a squared, I believe, is minus 1 over the concentration of A. So yes, and then from this, and then again a minus kt. Here, this, if you plug these in, we will get this A0, or the initial concentration, minus kt. And then to get the actual concentration, we should isolate it. So first just move this over. So 1 over this is KT plus 1 over alpha, the initial. Yes, that seems correct. And then putting or dividing by A0, we will get this term. And multiplying. And then just taking the inverse, we will get this, which seems to be correct. There are plots of these equations in the book if you want to look at them, but I don't really have time. Okay, so now on to case 2, we have 2 different types of reactant. So the order or the rate law will look like this term over here. Then there's another complexity to it, which is there's another case of if the concentrations of the 2 reactants are initially the same. So they're either the same or they're not. So if they're the same, then notice that one molecule of C requires 1 of A and 1 of B. So that means that B and A are used up at equal rates. So if we think of that, that should mean that the concentration of A and B should be the same for every time T. So then, well, this term just simplifies to, we can just write B, concentration of B in terms of A. So that will be this. And then that term is just another way is just to square. Okay. And then this should be, yes, the same as case 1, right? Because this term looks the same as this expression. Yes, so again, we will get this equation. So I will just steal this and move it over. Okay, yes. So in case 2b, I won't go into the details of this. There's a derivation in the book. But if the initial concentrations of the 2 reactants aren't the same, then you should do integration on this expression right here. And then you will get this expression over here. But it's not very important to know how to derive this. So as a recap, just remember that the equations for different orders. So for second order, it's a lot more complicated. You can divide it into either one reaction type or just 2 different reactants. And if there are 2 different reactants, you also have to consider the initial concentrations as well. But deriving the complicated formula over here is not really important. Okay, so another important topic is half-life of a reaction. So the half-life is the time that it takes for half of the initial reactant to be converted to product. So to solve for half-life, we just set the concentration of A to be, well, 1/2 of the initial concentration. And then plug this into the integrated forms of the reactions. So if you remember, a 0 order reaction has this term. So we just plug in the concentration of A to be half of the initial concentration. So that should look like this. So 1/2 of the initial concentration, and then minus A0. That is minus KT. And then this is the half-life because we're setting it to be half of the initial. This will be negative 1/2 the initial minus KT Okay, and then so if you rearrange this thing, then you will see that the half-life is this term over here. So it does depend on the initial concentration. So that's interesting, but I think the first order is more interesting. Here again, do the same thing, just plug in the half of the initial concentration. This will be 1/2. And then take the logarithm. So log, or well, ln probably helps, but okay. Minus, that will be just minus kt. But then notice that log of 1/2, that's the same as minus log of 2, since 1/2 is 2 to the minus 1. Yes. Am I doing this right? Yes. Yes. Okay. So, well, I should have put half just to represent this as half-life, but that's okay. So, yes, after rearranging, you should get this term over here. So why I find this interesting is that the half-life for a first order reaction doesn't depend on the initial concentration. And that's also why we use um, carbon for dating things. Yes. And then for a second order, I will just do the simple case of only one type of reactant. So 2A becomes 1C. So this. So again, we know that it's the integrated form is this equation. And then just do the usual thing, setting the concentration to be half of the initial. We have this term. So these cancel out, and then 1/2 is equal to 1 over 1 plus k times the time. I'm gonna set that equal to this. And then that tells us that 2, if I'm doing my math correctly, yes, 2 is equal to 1 plus k times the half-life times the initial concentration. So if you continue on with the math, you should get the half-life is 1 over k times the initial concentration. So just to wrap up, the half-life reactions, I noticed that for all of the orders except for the first order, they all depend on the initial concentration. Yes, and this is so far all I have. So I think it's almost time for the homework session. So thank you.